Right, theory of probability. Let's do this. So this is the Emma Dobson special request edition of theory of probability. So this is going to be the last lecture for this week, as Good Friday is on Friday. Really happy with where we are in the course right now. I do have a couple of topics that I'll hit on, mainly having to do with estimation of probabilities using expectations and whatnot. But if you go and you page through chapter 7, a lot of that material I've actually covered because it just felt more appropriate to cover it earlier on at certain moments than to kind of lump it all together. I wanted to give it to you in context. So if you page through there, you'll see what I mean. But there's a couple of topics that I might hit on, specifically conditional expectations involving random variables. I may look at a couple of examples of that. I may look at some probabilistic inequalities, like the Markov inequality, and maybe even Chernoff bounds, things like that. But if there's a specific topic that you would really like to see covered, please do let me know, okay? In case you missed it, I did post a homework quiz for you to complete by midnight on Thursday. So please go take care of that at your leisure. Okay, so that's due on the 9th, April 9th at midnight, okay? I gave that to you a little bit earlier than usual because it's Good Friday on Friday. I want you to enjoy the weekend. And hopefully you won't find the problem to be too arduous or anything. Okay, so Emma had requested, because I did give you a couple of problems on this, had requested that I specifically go over the material on kind of transformations of random variables. Now, this topic, depending on who you had Calc 3 with, sometimes this topic will be covered in a Calc 3 context, okay? But it doesn't matter if you saw this or not. We're going to kind of cover it in full detail here. But the idea here is, what do you do if you start with a couple of random variables? Okay, so like x1 and x2 are continuous RVs, okay, and they have joint density f sub x1 comma x2. All right, so that's our joint density for these two things. But what if I then go and actually come up with a couple of other random variables that are functions of x1 and x2, okay? So a couple of random variables that are actually functions of x1 and x2. Maybe it's a, some polynomial in x1 and x2. Maybe it's a ratio of x1 and x2. For whatever reason, I might have need to actually do something with x1 and x2. Like maybe I want to add them together, for instance, okay? So let's let y1 just be some function, okay? So g1 of x1 and x2, and y2 is going to be some other function of x1 and x2, okay? And the goal here is going to be what? Well, can I actually find the joint density for y1 and y2, right? So we want to find the density of y1 and y2, okay? Find the density of y1 and y2 given the above situation, okay? And there are specific things that we kind of have to assume about, for instance, like G1 and G2, namely that they behave nicely in some meaningful way, but we're not going to get into the specific details of that necessarily. So we basically just want to find this joint density right here, okay? So first of all, you know, you have these equations right here. Okay, that y1 and y2 are given by these two functions of x1 and x2. Okay, and what we need to do from these is we need to solve for x1 and x2 in terms of y1 and y2. Okay, so so what we're going to write for those is we'll write x1 is just going to be h1 of y1, y2, and x2 is going to be h2 of y1, y2. Okay. By the way, this whole business that we're dealing with right here really falls into a category called change of variables. Change of variables. Okay. You did this in Calc 2, believe it or not. I mean, you called it a substitution. A substitution is a form of a change of variable. You also did it, for instance, when you converted integrals into polar coordinates, okay? In Calc 3. You also did it when you converted triple integrals into spherical coordinates in Calc 3. Or when you converted double integrals into cylindrical coordinates or polar coordinates, that was a change of variables. Also, when you did trig substitutions in Calc 2, that was a change of variables. There was something general happening there that we're going to make explicit here. So again, you start with x1 and x2. You have this joint density f of x1, x2, and you want to see what change occurs in the density for y1 and y2 once you make this transformation. Okay. All right. So I'll go over to the next page here, and we'll keep on going here. Okay. I've just copied down the information. Again, we have two random variables that are continuous, right? These are continuous random variables. And we have the joint density f sub x1, x2. We have written y1 as a function of x1 and x2, and y2 as another function of x1 and x2. And the goal that we have in mind is what on earth is going on with the joint density for this new pair of random variables? Can I sort it out? And the first step toward doing that, again, was to solve for x1 in terms of y1 and y2. So this was what I called h1 of y1, y2. And x2 is h2 of y1 and y2, y1 and y2. Okay. And step 2, okay, and by the way, that's just a typical thing that you have to do. Look, in the end, if you want to eliminate x1 and x2 from everywhere, this is something you're going to have to do anyways. You're going to have to kind of reverse engineer x1 and x2 in terms of y1 and y2 in order to eliminate them from the thing that you're integrating. After all, the joint density is the thing you integrate to find various probabilities. Okay, and so what you're trying to do is you're trying to switch everything from being in terms of x1 and x2. You're trying to switch it over to being in terms of the new variable y1 and y2. Okay, so what is the second step here? Well, the second step is to compute this thing called, compute the so-called Jacobian of the transformation. Okay, so what is that? Well, it's this. Okay, so you call it J of, and we'll write little x's now. So J of x1, x2. Okay, and it's the determinant of the following 2x2 matrix. Okay, you take the partial of G1, with respect to x1, and you take the partial of g1 with respect to x2. It's the partial derivatives. Okay, you learn about that in Calc 3, remember? So you take the partial of the transformation with respect to x, and you take the x1, and you take the partial of the first function with respect to the second variable. Okay, and then next you take the partial of the second function with respect to the first variable, and you take the partial of the second function with respect to the second variable. Okay, and this is determinate. You may or may not remember what's going on with that, but what happens is you kind of multiply these two together and you subtract the product of these two things. Okay, that's what you do when you have a 2 by 2 determinant. You compute it slightly differently if you happen to have 3 variables, each of which were a function of 3 prior variables. You would have a 3 by 3 determinant in that case. You go partial with respect of the first function with respect to the first variable, first function with respect to the second variable, first function with respect to the third variable on the first row, and then you would proceed through each one of the rows. Okay, so what does this thing equal? Well, it equals, so partial g1 with respect to x1 times the partial of g2, partial derivative of g2 with respect to x2. Okay. And then you subtract the partial of g2 with respect to x1 and the partial of g1 with respect to x2. Okay, so that's what the so-called Jacobian of the transformation is. Okay, and once you have that, you're basically done. Okay. Because the third step in the process is to simply say, and you might say to yourself, where in the world does that Jacobian factor come from? Well, that gets into a little bit of linear algebra, okay, and some vector calculus, actually. I won't go into the details of that right now, but essentially this Jacobian right here is kind of detecting how the integral has been distorted by this transformation and how we need to adjust. And this Jacobian is kind of an adjustment factor. Okay, so like if I put u equal to x squared, okay, the distortion factor, if I want to write du, well, it's 2x dx, okay? The distortion factor is that 2x thing that happens to be there when you do that substitution in Calc 1. This is basically the price you pay for making this substitution. It's the Jacobian. Telling you the Jacobian of the transformations you were doing in Calc 2 were Jacobians just like what we're computing here, but they were like 1-by-1 matrices. You were computing determinants of. It was kind of silly. Okay. So what's the deal? Well, the joint density, right? We just have it. The joint density of f of y1, y2 of little y1, little y2 is going to be equal to what? Well, it's the density of the original two random variables, okay, of little x1, little x2, and then you basically take the absolute value, right? You multiply this by the absolute value of this Jacobian of the transformation, but then you actually have to invert this thing. And what about these? So here's a little question that I have for us here. What about these, the fact that there's x's over here, right? So there's an x and there's an x here, and there's an x1 and there's an x2 here. How do I get rid of those? Well, I know what x1 and x12 are in terms of y1 and y2, right? So I basically would use that here, 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 and here. Okay, that allows me to get rid of, right? So the point is that you eliminate the x's, right? So x1 and x2 with these equations. Okay, you simply just plug in what x1 and x2 are in terms of y1 and y2. okay? So again, there's nothing like super complicated going on here. It's really just a souped up version of what you did in Calc 2. Start with your two random variables. You have this joint density. You have a function of the two original random variables, and you want to know what the new joint density is for those new random variables that are functions of the originals. Okay? So what you have to do is you solve for the original random variables in terms of the new ones, okay? And then you compute the Jacobian of the transformation, and that uses the G's, okay? So, and then you basically, you know the formula for the new joint density. It's going to be the original joint density multiplied by the inverse of the Jacobian, where you've replaced x1 and x2 with what they are in terms of y1 and y2. So all that to say is now right, once you've eliminated the x's with the y's by using those two equations, you have a function that's completely in terms of the y's now. Okay, so it makes sense that would be the density. Okay, and again, the proof of this involves some vector calculus. It's not like super difficult, but it's not a place we really want to go right now. You just have kind of to trust the formula. The proof that you really need the Jacobian, it just involves kind of what happens when you do this transformation from the one set of coordinates to the other set of coordinates. What happens? And you just have to think it through a little bit, and that Jacobian keeps showing up as the price you pay. And again, you've already seen this in Calc 2 played out in a very simple way. All right, so let's go ahead and look at some examples.